Time only moves in one direction, and the reason is one of physics' greatest puzzles. The physicist Arthur Eddington called entropy times arrow, a mysterious link between disorder and the irreversible flow of our reality. This video will fundamentally change how you perceive time itself, revealing why the past feels so different from the future. We are going to explore why shattered glass never reassembles and how the entire cosmos might be winding down from a single, impossible starting point. Why can we only remember what has already happened? What cosmic rule ensures that time marches forward, never back? How does your own consciousness depend on this universal drift toward chaos? By the end, you will see the flow of time not as a simple fact, but as a profound physical phenomenon with staggering implications for everything from your memories to the fate of the universe. What does the one-way street of time mean for your own story? This directionality is so fundamental to our reality that we rarely stop to question it. We remember yesterday, but not tomorrow. A cup of coffee cools in your hands. It never spontaneously heats up. This is the arrow of time, a property of the universe that dictates a single, consistent direction from what was to what will be. It is not a force you can measure, but an undeniable feature of existence itself. Physicists actually identify several different arrows, all strangely aligned. There is the psychological arrow, our own internal experience of time flowing from past to future, the river of consciousness that carries our memories and expectations. Then there is the thermodynamic arrow, the one most famously linked to entropy, which points toward increasing disorder. Think of ice melting in a warm room, its structured crystals dissolving into chaotic water molecules. The process only goes one way. We also see a cosmological arrow defined by the expansion of the universe from a dense, hot beginning, and even a radiative arrow which explains why light waves spread outward from a star, never converging inward from empty space to create it. The profound mystery, as thinkers like Sean Carroll have emphasized, is why all these arrows agree. Why does the expansion of the cosmos match the increase in disorder, which in turn matches the direction in which we accumulate memories? This alignment is the first major clue that we are not just dealing with a quirk of human perception, but a deep physical law. The origin of time's one-way street appears to be rooted in a single, powerful concept: the relentless growth of chaos. This principle, the second law of thermodynamics, is the engine behind time's arrow. It declares a simple, universal truth. For any isolated system, the total amount of entropy, a measure of disorder, will always stay the same or increase. It will never, ever spontaneously decrease. Think about that drop of ink spreading through a glass of water. The ink molecules begin in a neat, ordered drop, a state of low entropy. They then drift and mingle, transforming the water into a uniform, hazy blue, a state of high entropy. You can watch this happen every day, but you will never, under any normal circumstances, see all those scattered ink particles suddenly decide to swim back together into a single, dense drop. The process is irreversible. This is not a suggestion. It is a fundamental law of our universe, as physicist Rudolf Clausius recognized when he named entropy. He stated that while the total energy of the universe is constant, its entropy is always striving toward a maximum. This relentless drive toward disorder is the most powerful and observable arrow of time we have. It governs the fate of everything, from a melting ice cube losing its crystalline structure to a star eventually burning out, its once concentrated fuel dissipated into the cold void of space. The universe, it seems, has a profound preference for chaos, but if the universe is always getting more disordered, Where did all the initial order come from? This question takes us back to the very beginning of everything. But what is this thing we call entropy, really? We often describe it as disorder, but that is just a metaphor. At its heart, entropy is a precise statistical measure. It counts the number of microscopic arrangements, the different ways all the tiny particles can be jumbled up that still look the same to our eyes. Think of your desk. A clean, organized desk represents a state of low entropy. There is only one, or maybe a few, specific ways for everything to be perfectly arranged. But a messy desk with papers and pens scattered everywhere is a state of high entropy. Why? Because there are countless ways for a desk to be messy. The system has simply found one of the overwhelmingly numerous disordered states. This statistical view was the brilliant insight of physicist Ludwig Boltzmann. He realized that the universe does not favor disorder out of some strange preference. It favors disorder because disordered states are infinitely more probable. A system evolves from a less likely, ordered state to a more likely, disordered one for the same reason a dropped deck of cards is more likely to scatter across the floor than to land in a perfectly stacked pile. There are just so many more ways to be messy than to be neat. This relentless statistical drift, this stumbling from one improbable state into a sea of probable ones, is the true engine of the second law. It is not a force that prohibits order, but a simple rule of probability that makes disorder the expected outcome. This is why processes are irreversible and why time has a definitive arrow. The universe is not running backward because it is forbidden, but because returning to a state of perfect order is statistically almost impossible, like expecting a vast ocean of randomly scattered puzzle pieces to suddenly assemble themselves into a single, perfect picture. This statistical view reveals a stunning implication for the cosmos. If the universe is always stumbling toward more probable, disordered states, then it must have begun in an astoundingly improbable state of order. This is the past hypothesis, the idea that our entire reality started with an impossibly low entropy. The primordial universe was not a formless, chaotic soup. It was, paradoxically, a place of exquisite and specific arrangement. Think of the Big Bang not as a violent explosion of randomness, but as the ultimate act of meticulous organization, a cosmic deck of cards perfectly stacked and ready to be shuffled. Cosmologists like Roger Penrose have tried to quantify just how special this starting point was. The probability of the early universe having such a low entropy is a number so small it defies human comprehension, far less likely than randomly selecting a single, predetermined atom from the entire visible cosmos. This beginning was the ultimate wound-up spring, a state of pure potential that has been unwinding ever since. The entire history of our universe, from the formation of galaxies to the brewing of your morning coffee, is just the long, slow release of that initial tension. The increase in entropy is not the engine of time, but the exhaust, the visible trail left behind as this cosmic spring uncoils. Yet the laws of physics we know do not predict or explain this special starting state. The equations work just as well backward as they do forward. The past hypothesis is not a law but a boundary condition, a single, monumental fact about our particular universe. It is the one-time setup that gives time its arrow, pointing us back to a mysterious origin we do not fully understand. Why was the universe born with such perfect, improbable order? The answer to that question may hold the key to why we remember yesterday, but not tomorrow. This paradox cuts to the very heart of our mystery. The fundamental laws governing particles are completely blind to the direction of time. If you were to film two atoms colliding and then play the recording backward, you would not be able to tell the difference. the event is perfectly time-symmetric. The equations of Newton, Einstein, and even quantum mechanics work identically whether time flows forward or backward. There is no built-in past or future. So why does our world of experience, built from these very particles, possess such a definite and irreversible arrow? The answer lies not in the laws themselves, but in the staggering power of large numbers. Consider the journey of a single air molecule in your room. Its path is a chaotic zigzag of countless collisions. In principle, if you could reverse the velocities of every single particle involved in its journey, that one molecule would retrace its exact path backward. The microscopic laws would permit it. Now, try to imagine applying that reversal to every one of the trillions upon trillions of air molecules, dust particles, and even the molecules in the walls themselves. The probability that all of them would spontaneously and simultaneously coordinate their motions to reverse their paths is not just small. It is so infinitesimally tiny that for all practical purposes, it is impossible. This is the chasm between microscopic reversibility and macroscopic irreversibility. Physicist Richard Feynman offered a beautifully simple analogy. Take a brand new deck of cards perfectly ordered by suit and sequence. A single shuffle completely randomizes it, scattering the cards into one of an astronomical number of possible disordered arrangements. This is the inevitable, high-probability outcome. Now, could a subsequent shuffle accidentally restore the deck to its original, perfect order? Theoretically, yes. But the odds are so overwhelmingly against it that you could shuffle cards for the entire lifetime of the universe and never expect to see it happen. The arrow of time emerges from this statistical reality. We do not see shattered glass reassemble because it would require every single fragment to spontaneously leap from the floor, navigating a perfectly coordinated reverse trajectory through the air to seamlessly fuse back together. The fundamental laws of physics do not forbid this event. The sheer, mind-boggling improbability of it does. Time's arrow is not written into the laws of the tiny, but is a breathtakingly powerful illusion conjured by the collective behavior of the whole. So if our experience of time is a statistical mirage, what does that mean for the flow of our own consciousness? This statistical dominance is the true architect of our one-way reality. Ludwig Boltzmann formalized this idea with his H-theorem, a mathematical argument showing how countless random collisions between molecules inevitably drive any system toward its most probable state. The universe does not choose disorder. It simply stumbles into it again and again because the path to chaos is paved with an infinite number of possibilities. Picture a sealed box with a partition down the middle. On one side, you have a gas like nitrogen, and on the other, a gas like oxygen. These are two ordered, separate systems. The moment you remove that partition, you unleash a storm of probability. The molecules begin to fly and collide, their paths a tangled web of chaos. There is only one specific microscopic arrangement where all the nitrogen is on its original side and all the oxygen remains on the other. But there are countless trillions upon trillions of arrangements where the two gases are thoroughly and completely mixed. The system is not actively seeking out mixture. It is merely wandering blindly through all the possible ways its particles can be arranged, and since the mixed states outnumber the unmixed states by an unimaginable margin, finding a mixed state is a virtual certainty. This is the probabilistic engine of the second law. The arrow of time emerges from this relentless, random walk toward the statistically dominant configuration. The fundamental laws governing each individual collision are perfectly reversible, yet the collective outcome is a one-way street. How can something so definite arise from something so random? The answer lies in the sheer power of scale. A single molecule bouncing around might occasionally find its way back to its starting point, but for an entire gas with its unimaginable number of particles, the coordinated motion required for everyone to turn around and go home is so statistically monstrous that it is effectively forbidden by the weight of numbers alone. This is the profound break in symmetry. The microscopic world is blind to past and future, but our macroscopic reality is utterly enslaved to it, not by force but by probability. Our very experience of a flowing, irreversible time is a grand illusion woven from innumerable reversible events. So if time is a statistical phenomenon, what does that imply for the ultimate fate of everything? But the story of entropy does not end with gases and shattered glass. It is also a story about information itself. In the middle of the 20th century, a mathematician and engineer named Claude Shannon made a revolutionary discovery. He was working on the problem of sending messages over telephone lines, and he needed a precise way to measure information. What he developed was a mathematical formula for information entropy. In this context, entropy is not about physical disorder, but about uncertainty. A high information entropy message is one that is unpredictable, full of surprise. A low entropy message is completely predictable and tells you nothing new. Think of a string of letters. If I tell you the next letter is always Q, the sequence has very low entropy and carries almost no information. But if the next letter could be anything, the entropy is high, and every new letter you receive gives you a genuine piece of information. This creates a profound and beautiful parallel. A physically ordered state, like that perfectly stacked deck of cards, is also a state of low information entropy. If you know the deck is new and ordered, you have complete information about the location of every card. The messy, shuffled deck is a high entropy state both physically and informationally. You are highly uncertain about where any specific card might be. The act of gaining information is directly tied to this increase in entropy. Consider a simple act of observation. To see something, light particles or photons must bounce off the object and enter your eye. That interaction is not a clean, perfect transfer. It is a physical process that inevitably increases the total entropy of the universe, perhaps by dissipating a tiny amount of heat. Every time you learn something new about the world, every time you reduce your own personal uncertainty, you are, in a small way, contributing to the universal drift toward disorder. Your consciousness, your very process of accumulating knowledge and memories, is coupled to the thermodynamic arrow. The flow of information and the flow of time become two sides of the same cosmic coin. We are not passive observers of the universe's journey from order to chaos. Our attempts to understand it, to gather information and build knowledge, are themselves part of that very journey. This bridge between physics and computation suggests that the arrow of time might be fundamentally woven into the fabric of what it means to know and to remember. So if our quest for knowledge is tied to the increase of entropy, what does that imply for the ultimate fate of all information in the cosmos? This link between information and entropy brings us to the very nature of our own minds. Why is it that we remember the past so clearly, yet have no memories of the future? The answer is not just philosophical, it is deeply physical. Your brain, the organ of your consciousness, is not a magical exception to the laws of the universe. It is a physical system made of atoms, and every single thought you have, every memory you form, is a physical process. When you experience an event, neurons fire in specific patterns, chemicals are released, and new connections are forged. This intricate dance is a cascade of physical changes, and like any other physical process, it generates heat and increases the overall disorder of the universe. To form a memory is to create a record, a kind of indelible mark upon your neural circuitry. And creating that record, just like writing on a piece of paper, requires energy and produces waste, increasing entropy. Think of a memory as a footprint in the sand. The footprint is a structured, low-entropy pattern that tells a story about the past. But to make that footprint, you had to disturb the smooth, high-entropy randomness of the sand. The act of creating order in one place, your memory trace, always creates more disorder in the surroundings. This is the crucial one-way relationship. We can only have memories of events that have already happened because those events are in our past, lower entropy state. A memory of a future event is physically impossible. It would be like a footprint appearing in the sand before anyone has walked there, a structured pattern emerging from nowhere, which would mean a spontaneous and impossible decrease in entropy. Our very perception of time flowing from past to future is a direct consequence of the universe's relentless thermodynamic evolution. Your stream of consciousness, your accumulation of experiences and knowledge, is not just happening within time. It is a living, breathing manifestation of the second law itself. You are not merely observing the arrow of time. You are the arrow, a continuous process of turning the ordered potential of the past into the informed but disordered reality of the present. This profound merger of physics and subjective experience suggests that our minds are not separate from the cosmos, but are active participants in its grand, irreversible narrative. The same cosmic drive toward disorder that shapes our minds also sculpts the universe on its grandest scales. Look up at the night sky, and you are witnessing another fundamental arrow of time, the cosmological arrow defined by the expansion of the universe itself. Galaxies are not static islands in space, they are flying apart from one another, carried on the stretching fabric of space-time. This expansion is not just a detail of cosmology, it is the ultimate stage upon which the drama of entropy unfolds. In the beginning, the universe was an incredibly hot, dense, and smooth soup of particles. This might sound chaotic, but for gravity, this uniformity was a state of remarkably low entropy. A perfectly smooth distribution is actually highly ordered and improbable. Gravity abhors this uniformity. It seized upon the tiniest of fluctuations and began a work of cosmic sculpture, pulling matter together to form the first stars and galaxies. This clumping was a local decrease in gravitational entropy, a creation of stunning order from a smoother past. But this local ordering came at a cost paid in thermal entropy. As gas collapsed to form stars, it heated up to incredible temperatures, triggering nuclear fusion. These stellar engines then radiated that intense heat out into the cold emptiness of space, a massive and irreversible increase in disorder. The brilliant light from a star is not just energy, it is the exhaust of a gravitational engine, the universe trading gravitational order for thermal chaos. The expansion of space itself provides the necessary gradient for this entire process. It is the ever-cooling background that allows heat to flow, the ever-widening arena that lets gravity build its structures. Without this expansion, the universe would have quickly reached a bland, lukewarm equilibrium, a state of maximum entropy where nothing interesting could ever happen again. It is the ongoing expansion that sets the stage for the continuous battle between gravity's drive to create order and thermodynamics' demand for ultimate disorder. This cosmic tension is what carved out the galaxies, ignited the stars, and ultimately created the conditions where life and our own conscious experience of time could emerge. The universe's grandest motion and the tiny rules of disorder are two expressions of the same underlying reality. So if the expansion of space is so crucial to the arrow of time, what happens when this expansion reaches its final, chilling conclusion? Yet this cosmic expansion is not the final word on disorder. Black holes represent the ultimate victory of gravity, and they hold a paradoxical secret. They are not just cosmic vacuums, they are the single most entropic objects in the known universe. A black hole is chaos perfected, a point of no return where gravity has crushed matter into its most profoundly disordered state. This incredible insight came from the work of physicists Jacob Bekenstein and Stephen Hawking. They calculated that the entropy of a black hole is not proportional to its volume, as you might expect for a three-dimensional object, but to the surface area of its event horizon, the invisible boundary from which not even light can escape. Think about that for a moment. The amount of chaos, the ultimate disorder contained within a black hole, is written on its two-dimensional surface. This is a radical idea. It suggests that all the information about what fell into the black hole, every star, every planet, every atom, is somehow encoded on its boundary, not stored within its vast interior. It is as if the entire three-dimensional content of a room could be perfectly described by an intricate painting on its walls. This discovery, the Bekenstein-Hawking formula, was a shock to physics, pointing toward a deep connection between gravity, quantum mechanics, and information, a key puzzle in the quest for a theory of everything. But the story of black holes and entropy does not end there. Hawking made another stunning prediction that black holes are not truly black. Due to quantum effects near the event horizon, they slowly leak radiation, a faint glow now known as Hawking radiation. This process causes the black hole to gradually lose mass and energy, slowly evaporating over astronomical timescales. The formation of a black hole is a massive increase in entropy, a star collapsing into the ultimate state of gravitational disorder. Its slow evaporation via Hawking radiation is also a process that increases the overall entropy of the universe, as the energy and information are slowly and chaotically released back into the cosmos. But this creates a profound puzzle, the black hole information paradox. The fundamental laws of quantum mechanics state that information can never be truly destroyed. Yet if a black hole evaporates completely, what happens to all the detailed information about the things that fell in? Is it lost forever, violating a core principle of physics, or is it somehow preserved in the Hawking radiation in a scrambled, unrecognizable form? This paradox forces us to confront the limits of our current understanding, pushing the laws of physics to their breaking point in an environment where gravity is king and the arrow of time faces its ultimate test. Yet the mystery of time's arrow deepens as we descend into the quantum realm. The rules governing the smallest particles in the universe present us with another profound puzzle. Quantum mechanics describes a world of fuzzy probabilities where particles exist in a blend of all possible states, a condition known as a wave function. The truly strange event occurs when we measure such a system. In that instant, the wave function appears to collapse and the particle snaps into one definite state. This act of measurement seems to be a fundamentally irreversible process, creating a distinct quantum arrow of time. We see a definite result in the present, but the fuzzy superposition of possibilities is lost to the past. The underlying mathematical equation, the Schrödinger equation, is perfectly time-symmetric. It shows no preference for past or future. So why does the act of observation seem to break this symmetry, forcing a single, concrete reality to emerge from a sea of maybes? This is the famous measurement problem, and its resolution may be the key to understanding how our definite, classical world is built from such uncertain quantum foundations. One compelling interpretation, the many worlds hypothesis, offers a radical solution. It suggests that the wave function never actually collapses. Instead, at the moment of measurement, the universe splits. Every single possible outcome of the quantum event actually occurs, but in a newly branched parallel reality. What you perceive as a single, definite outcome is simply the one your branch of reality has become correlated with. Your measuring device, your eyes, your brain all become entangled with one specific result. This process of becoming entangled, of spreading quantum correlations, is what physicists call decoherence. And this process carries its own version of entropy, a measure of the quantum information and correlations spreading out into the environment. This growth of entanglement entropy is a one-way street. Once a system becomes entangled and decoheres, it cannot spontaneously reverse and become pure and isolated again. This provides a powerful new perspective on time's arrow. The flow of time we experience may be fundamentally linked to this relentless growth of quantum connections. As particles interact with each other and with their environment, their individual quantum identities become lost in a vast, correlated web. This irreversible spreading of information and correlation is what solidifies the fuzzy quantum world into the concrete reality we perceive. It is the process that turns possibility into actuality, and in doing so, it may be the common thread that weaves together the microscopic quantum arrow and the macroscopic thermodynamic arrow into a single, unbreakable flow. Life presents the most stunning defiance of the arrow of time. A towering redwood tree, a hummingbird, the double helix of your own DNA. These are all structures of breathtaking order, islands of complexity in a universe supposedly sliding toward chaos. How can life build such intricate, low-entropy forms while the second law commands an increase in disorder? The answer is that life does not violate this cosmic rule. It cleverly sidesteps it by becoming an engine for chaos elsewhere. Every living thing is a local organizer that globally accelerates the universe's drift toward disorder. A plant is a perfect example. It captures the disordered, high-entropy light from the sun. It then uses that energy to perform the miraculous work of photosynthesis, building structured sugars and complex molecules from simple carbon dioxide and water. This creates a pocket of exquisite order, but the plant is not a closed system. For every bit of order it creates within its leaves and stems, it expels far more disorder into its environment. It radiates waste heat back into the atmosphere, and it consumes orderly molecules only to release simpler, more disordered ones. The plant is a tiny, temporary rebellion against entropy, but its very existence depends on increasing the total entropy of the universe at an even faster rate. Evolution itself is a grand expression of this principle. It is a process that explores the landscape of biological possibility, creating vast amounts of information and complexity in the form of genetic codes and intricate ecosystems. But this exploration is fueled by a constant, raging torrent of energy from our sun, a flow that allows for local increases in order only by generating a far greater wave of disorder in its wake. Life is not a paradox, it is a beautiful, complex whirlpool in the great river of cosmic chaos, a temporary structure that can only persist as long as the energetic current flows through it. This intimate connection between life and entropy leads to an even more personal mystery, the nature of our own conscious will. Your feeling of making a choice, of deliberating between options and selecting a path forward, is a direct experience of the arrow of time in action. In a universe where past and future were symmetric, where cause and effect could run in either direction, the very idea of choice would be meaningless. Your decisions would be mere waypoints in a predetermined loop, not actions that genuinely shape an open future. The feeling of agency, of being the one who steers your life, depends entirely on the universe having a definite, irreversible timeline. Some thinkers, like the physicist Roger Penrose, have ventured a fascinating possibility. They suggest that the murky, probabilistic world of quantum mechanics, with its inherent uncertainties, might be the very thing that allows for genuine free will. The idea is that quantum processes within the brain could introduce an element of non-determinism, a tiny seed of true randomness at the neuronal level, which our consciousness then amplifies into what we perceive as a deliberate choice. Whether or not this specific theory holds, the broader point is profound. The very feeling of now, the vivid present moment in which you make your decisions, may be an emergent property of a brain operating within a thermodynamic environment where entropy is relentlessly increasing. Your brain is a physical system constantly processing information, forming memories, and making predictions. This entire operation requires energy and generates heat, contributing to the universal rise in disorder. Your conscious experience is not a ghost in the machine, but the dynamic, flowing state of a complex biological system that is itself a manifestation of the second law. Your sense of self, your ability to act upon the world and change it, is woven from the same cosmic fabric as a star radiating light or a river carving a canyon. Your free will is not an illusion that physics must explain away, but rather a feature that emerges in a universe with a definite past and an undetermined future, a universe that is still writing its story. This suggests that our deepest personal experiences of choice and consciousness are not separate from the cosmos, but are direct, intimate expressions of its most fundamental rule. This brings us to a deep and troubling puzzle known as the Loschmidt paradox. The fundamental laws of physics are perfectly reversible, like a movie that could be played backward without breaking any rules. For every process we see where entropy increases, like a cup shattering on the floor, there should be a valid, time-reversed version where entropy decreases, with the fragments flying up from the ground to seamlessly reassemble into a whole cup. The equations of motion allow for this. So why does our reality show us only one version of the film? The resolution lies not in the laws themselves, but in the staggering unlikelihood of the initial conditions required for the reverse process. Think of it like this: you can drop a single marble onto a hard surface and watch it bounce. The path it takes on the way down is perfectly mirrored by its path on the way up. This is a simple, reversible event. Now, imagine trying to coordinate the reverse path for a shattered cup. It would require every single one of the countless fragments, down to the tiniest splinter, to launch upward at the exact right instant, with the precise velocity and angle, to perfectly recreate the moment of impact in reverse. The fundamental laws do not forbid this. The probability of it happening, however, is so infinitesimally small that it is effectively zero. This is where the past hypothesis returns with immense power. Our universe started in a state of incredibly low entropy, a condition of exquisite and specific order. This unique starting point acts like a cosmic anchor, fixing the direction for everything that follows. It effectively chooses the arrow of time by providing a past that is radically different from the future. All the processes we see, from the expansion of a gas to the firing of your neurons, are just statistical consequences of this one-time, special beginning. In a hypothetical universe that did not begin with such a low entropy state, there would be no consistent arrow of time at all. Events would fluctuate randomly, with cups sometimes shattering and sometimes reassembling, and memories could form of both the past and the future. Our experience of a uniform, flowing time is a direct gift from that singular cosmic origin. The Loschmidt paradox forces us to accept a profound truth. The laws of physics are not enough to explain the world we see. We need a specific history, a unique cosmological context, to account for the overwhelming asymmetry between past and future. The arrow of time is not written into the equations of motion, but into the very first moment of our universe's story. this ultimate destination is the universe's final, chilling state of rest known as the heat death. It is the logical endpoint of the second law's relentless drive, a cosmos where entropy has finally reached its maximum value. Imagine a vast, dark ocean where every last wave has been smoothed away, leaving behind only a perfectly flat, motionless sea stretching to infinity. In this distant future, the universe will have exhausted all its potential for change. All energy will be uniformly distributed, a condition known as thermal equilibrium. There will be no hot spots and no cold spots, no useful temperature differences anywhere. The temperature of the entire cosmos will approach absolute zero, the point where all molecular motion ceases. In such a state, no work can be done, no engine can run, no star can shine, and no thought can form. It is the end of all processes, the final, silent victory of disorder over form. This is not a violent end, but a slow, inexorable fade into a uniform, featureless equilibrium. Every star, from the mightiest blue giant to the faintest red dwarf, will have long since burned through its fuel, its fires extinguished. The galaxies will be dark, their stellar furnaces cold. Even the black holes, those ultimate monuments to gravity's power, will not endure forever. Over trillions upon trillions of years, they will slowly evaporate through Hawking radiation, their immense mass dissolving into a faint, final whisper of energy that disperses into the void. The universe will become a thin, ever-cooling soup of fundamental particles and radiation, spread so thinly that no two particles may ever interact again. This is the ultimate expression of time's arrow, the final, irreversible state toward which our entire cosmic story is flowing. Yet, this sobering prediction gives profound meaning to our present moment. We exist in a temporary golden age, a fleeting sliver of cosmic time nestled between the low-entropy fire of the Big Bang and the high-entropy cold of the heat death. It is only in this brief window that the universe is out of balance, filled with energy gradients and temperature differences that allow for the formation of complex structures. Stars can only burn because there is a cold space to radiate into. Life can only exist because it can consume orderly energy from the sun and expel disorder. Your very consciousness is a phenomenon of this transitional era, a spark of awareness made possible by the universe's ongoing, irreversible slide from order to chaos. The heat death is not just an end, but a frame that gives cosmic significance to the vibrant, dynamic, and precious now. Our universe's arrow feels absolute, but physics dares to ask a deeper question. Could the flow of time be different elsewhere? In the vast speculative landscape of the multiverse, other cosmic domains might possess entirely different initial conditions. If our arrow of time was set by a low-entropy beginning, another universe born from a more chaotic or differently arranged state might exhibit no clear arrow at all, or even one that flows backward from our perspective. In such a realm, shattered glass might routinely reassemble, and beings might remember tomorrow while anticipating yesterday. This is not mere science fiction, but a logical extension of cosmological models that take the laws of physics seriously. Some theories even propose a cyclical or bouncing universe where a great collapse leads to a new Big Bang. At that moment of maximum compression, a cosmic bounce, the arrow of time might theoretically reverse. The long slide into disorder that defined the old universe's history would flip, and a new era of rising order would begin from that point. Imagine the entire cosmic story, from galaxies to conscious beings, playing out in reverse from one cycle to the next. These ideas challenge the very uniqueness of our experience, suggesting that the relentless forward march we take for granted could be a local and temporary phenomenon. Further clues come from the strange symmetries of particle physics. The CPT theorem states that the combined operations of reversing charge, parity, which is like a mirror reflection, and time, should leave any physical process invariant. This profound symmetry suggests that a universe where all particles are replaced by their antimatter counterparts, reflected in a mirror and with time running backward, would behave exactly like our own. Yet, subtle experiments show that this perfect symmetry might be broken. Certain rare subatomic processes involving the weak nuclear force do not behave the same way when time is reversed. This tiny violation of time symmetry hints that the arrow of time might be woven into the most fundamental laws of matter, not just a statistical accident. It is a faint but tantalizing clue that the past and future are not perfectly equivalent, even at the level of individual particles. Exploring these speculative frontiers stretches our understanding to its limits. Our experience of time's arrow, so fundamental to every thought and memory, might be just one possible configuration in an infinitely richer cosmic tapestry. It invites us to look beyond our local reality and ponder a truly alien concept, a cosmos where the river of time flows in many different directions, or perhaps not at all. This fundamental asymmetry between past and future forces us to reconsider the very nature of reality. A popular view in physics and philosophy is the block universe, a model where time is a fourth dimension and the past, present, and future all exist simultaneously in a static, unchanging block. Every moment from the Big Bang to the heat death is just as real as a fixed point on a timeline. But if this is true, why does the past feel so concrete and the future so open? The relentless increase of entropy provides a powerful challenge to this idea. It suggests the block universe might be a mathematical illusion, a description that ignores the most important feature of our experience, the objective difference between what was and what will be. Philosopher Hugh Price has argued that the arrow of time is not a fundamental feature of the world but merely a perspective, a way that conscious beings like us happen to view the cosmos. Yet the physics of entropy pushes back, insisting that the difference is real and physical. The cause of an event is always in a lower entropy state than its effect. A lit match, an ordered bundle of chemical energy, causes a fire, which is a far more disordered and chaotic release of heat and light. This sequence is not just a matter of our perception. It is written into the fabric of events by the second law, giving a firm physical basis to the concept of causation. Without this thermodynamic arrow, the very idea of one thing causing another would lose its meaning. The universe would be a collection of correlated events with no inherent direction, a place where a fire could just as easily cause the unburning of a match. Our deepest intuition that causes must come before their effects is not a human construct, but a direct reflection of the universe's journey from order to chaos. This thermodynamic grounding of causality extends to our own sense of self. Your personal identity is not a static object, but a process, a story that unfolds in one irreversible direction. You are the same person you were a moment ago, not because some immutable soul persists, but because you carry the marks of your past. Your memories are a thermodynamic record, physical imprints on your brain that could only form in a universe with a definite past. Every new experience, every decision you make, adds another layer to this accumulating narrative, a process that is thermodynamically costly and fundamentally irreversible. You are a collection of stories written by time itself, a continuous thread woven from countless interactions that have increased the universe's total disorder. If time's arrow were to vanish, so too would the coherent story of you. Your identity depends entirely on this cosmic context, making you a living, breathing product of the universe's thermodynamic history. So if our reality and our very selves are so deeply tied to this one-way flow, what does it mean that the laws of physics themselves seem to allow for the possibility of its reversal? These cosmic rules of disorder govern the machines that power our modern world. Every engine, from the one in your car to the vast turbines in a power plant, is fundamentally constrained by the second law of thermodynamics. They operate by creating a flow of heat from a hot source to a cold sink, and in that flow they can extract useful work, but the process is inherently wasteful. The brilliant French engineer Sadi Carnot realized that there is an absolute, unbreakable limit to an engine's efficiency, a ceiling set not by engineering, but by the cold mathematics of entropy. The Carnot cycle defines this perfect, unreachable ideal. It shows that no matter how clever our designs become, a portion of the heat energy must always be rejected into the colder environment, lost forever as useless waste. This is not a flaw in our machinery. It is a fundamental decree from the universe itself. You cannot build a perfect engine because to do so would require a process that does not increase the total entropy, and that is forbidden. Our entire energy infrastructure, from fossil fuels to nuclear reactors, is a testament to our struggle to work within this cosmic constraint, squeezing out as much useful work as we can from every flow of heat that inevitably increases universal disorder. This relationship between energy and information becomes even more critical inside the very device you might be using right now. Every computation, every calculation performed by a computer is a physical act. In the 1960s, physicist Rolf Landauer made a startling discovery. He realized that it is not the process of computation itself that is thermodynamically costly, but the act of erasing information. When a computer erases a single bit of data, resetting it to a zero, it is effectively throwing away information about its previous state. And according to Landauer's principle, that lost information must be paid for with a corresponding increase in entropy, released as a tiny, unavoidable puff of heat. There is a fundamental lower limit to the energy required for computation, a barrier set by the second law. This principle is why our computers and data centers generate so much heat and consume vast amounts of electricity for cooling. We are literally fighting against the entropy cost of forgetting. This insight is now driving a frontier of computer science known as reversible computing, which imagines processors that could, in theory, avoid this energy penalty by never erasing information, instead running calculations backward to recover energy. While still largely theoretical, this pursuit shows how our deepest understanding of cosmic law is guiding the future of our most essential technology. From the hum of a refrigerator, which works by pumping heat from its cold interior to your warm kitchen, to the glow of a light bulb converting orderly electrical energy into disordered light and heat, our civilization is a grand, intricate dance with entropy. We are masters of chaos not because we can stop it, but because we have learned to channel its inevitable increase. We build local pockets of order, our cities and our machines, by creating even greater swells of disorder elsewhere. The electricity that powers your home likely came from a process that heated a river or warmed the atmosphere. The food in your refrigerator was preserved by a pump that made your kitchen slightly warmer. We are forever borrowing order at a steep interest rate of cosmic disorder. This is the profound, practical truth of our existence. The same law that ensures time's arrow flies in one direction, that gives us our memories and our sense of self, also dictates the ultimate limits of our innovation and the very cost of building a complex world. Our journey to understand entropy began with shattered glass and the fate of the cosmos, but it ends in the palm of your hand with the phone that grows warm with use, a daily, tangible reminder that you are living in and contributing to the universe's great irreversible story. This quest to unify the cosmic and the quantum is where our understanding of time faces its ultimate test. General relativity paints a magnificent picture of space-time as a smooth, dynamic fabric, while quantum mechanics reveals a frenetic, probabilistic world beneath. Unifying these two pillars into a single theory of quantum gravity is the greatest challenge in physics, and any successful theory must have something profound to say about the arrow of time. How can a direction be woven into the very fabric of a universe that may be fundamentally timeless? Some approaches, like loop quantum gravity, suggest that space and time are not smooth continua but are composed of tiny, discrete grains. In this view, the smooth flow of time we experience could be an illusion, much like a movie appearing continuous despite being made of individual frames. The arrow of time might then emerge from the way these fundamental quanta of space-time become entangled and correlated with one another, creating a net direction of change from the bottom up. String theory, another leading candidate, also operates in realms where our everyday notion of time breaks down. In its intricate landscape of extra dimensions and vibrating strings, the familiar distinction between past and future may not be fundamental. Instead, time's arrow could be a consequence of our particular position within a vast multiverse, a local phenomenon in a broader reality that is itself timeless. This idea of emergence is radical. It suggests that time itself is not a primary ingredient of the cosmos, but a secondary property that arises from something deeper, a vast, timeless network of relationships. Think of the way temperature emerges from the frantic motion of molecules. No single molecule is hot or cold, yet their collective dance creates the property we call temperature. In the same way, our relentless flow of time from past to future might emerge from the complex interactions of countless fundamental entities in a substrate where time, as we know it, does not exist. This forces us to generalize our concept of entropy once more, applying it to the fabric of space-time itself. The holographic principle, born from the study of black holes, offers a breathtaking vision. It proposes that all the information describing our three-dimensional universe, including every event that unfolds within time, could be encoded on a two-dimensional boundary surrounding it, like a cosmic DVD. The three-dimensional world we experience with its flowing time would then be a projection from that encoded surface. In this picture, the increase of entropy we associate with time's arrow might be linked to how information spreads and becomes entangled on this ultimate cosmic screen. Resolving the nature of time within a complete theory of quantum gravity could finally answer the question that has haunted us from the start. It might explain why the past hypothesis was true, why our universe began in that astoundingly improbable state of low entropy. The arrow of time would not be a separate, mysterious boundary condition slapped onto the laws of physics. It could be a derivable consequence, emerging naturally from the first principles of a final theory. The one-way street of our reality, from the shattering of glass to the firing of your neurons, might not be a starting assumption, but the ultimate conclusion. The universe did not have to begin with such perfect, improbable order. This single fact, the past hypothesis, feels less like a law of physics and more like a cosmic favor. Why was the deck of cards so perfectly stacked at the start? This question pushes past science into the realms of philosophy and theology, forcing us to confront the ultimate why. The initial low entropy of our cosmos appears to be a staggering example of fine-tuning, a one in an infinity setup so precise it seems almost intentional. Without this specific, delicate starting state, the arrow of time would not point consistently forward. There would be no galaxies, no stars, no planets, and certainly no beings capable of wondering about their own existence. The very fact that we are here to ask the question is a direct consequence of that special beginning. Some physicists, like Sean Carroll, offer a naturalistic explanation rooted in the multiverse. In an infinitely vast and varied cosmic landscape, with countless universes bubbling into existence, a few will inevitably, just by sheer chance, pop into being with the low entropy required for a long and interesting history. In this view, we simply find ourselves in one of the lucky ones, a universe where the conditions were just right for time to flow and life to emerge. Others see it as a brute fact, a foundational given with no deeper explanation. It is simply the way our universe is. This fine-tuning is not a minor detail. It is the absolute prerequisite for everything we hold as real. The arrow of time is the channel through which complexity can flow. It allows for the formation of intricate structures, from the spiral arms of a galaxy to the neural pathways in your brain. We are not just observers of this fine-tuned cosmos. We are products of it. Our consciousness, our ability to investigate the laws of nature, is a direct result of that initial wound-up spring of order slowly unwinding. We are living, breathing evidence of a very special cosmic starting point. The profound link is this: our capacity to ponder the Big Bang is a direct gift from the Big Bang's own improbable nature. We are the universe awakening to contemplate its own mysterious origin. Your own sense of the present moment, that fleeting now you are experiencing, is deeply entwined with this cosmic drift toward disorder. Consider what happens when you hear a sudden noise. The sound waves travel to your ears, triggering a cascade of neural signals that race toward your brain. This raw data is chaotic and unstructured. Your brain must then process it, comparing it to memories and expectations to identify the sound as, say, a slamming door. This act of processing, of transforming disordered sensory data into a coherent perception, is a physical operation that consumes energy and increases entropy within your neural circuitry. The famous specious present, that brief window of about 3 seconds that we perceive as a single moment, may be the precise timescale over which this cognitive updating occurs. It is the duration required for your brain to gather, process, and integrate information into a stable model of reality. This creates a rolling window of awareness, a continuous loop of taking in chaotic input and producing a momentary slice of order, which we then label as the present. The vivid feeling that time is flowing, that one moment seamlessly gives way to the next, could be the direct psychological experience of this relentless, entropy-generating processing in your brain. Your consciousness is not a passive spectator to time's river, but is itself the very current, a continuous act of turning the unknown future into the ordered, understood past at the cost of increasing the universe's total chaos. The flow of time is not just something you observe, it is something you actively create with every thought, every sensation, and every memory you form. This same thermodynamic arrow carves its path through the most complex systems in our world. Consider a thunderstorm gathering on the horizon. It forms through a chaotic dance of rising warm air, condensing moisture, and swirling winds, a process that consumes vast amounts of solar energy. Once it has raged and dissipated, you will never see that storm spontaneously reform, drawing its scattered rain and dissipated clouds back into a single, towering cloud. The storm's life is a one-way street. This irreversibility is woven into every complex system we know, from global weather patterns to the intricate web of a forest ecosystem. A species once evolved does not unevolve back into its ancestors. A fallen tree decomposes into soil, nourishing new life, but that soil will not reassemble itself into the exact same tree. These systems are all far from equilibrium, sustained by a constant flow of energy that allows them to build and maintain temporary structures of incredible intricacy. They are inherently historical, their present state a unique record of everything that has happened to them. This is where a famous idea takes hold, the butterfly effect. The notion that the flapping of a butterfly's wings in Brazil could set in motion a chain of events that ultimately influences a tornado in Texas is more than a poetic metaphor. It highlights a fundamental property of complex systems, their profound sensitivity to initial conditions. The tiniest, most unmeasurable detail in the starting state can lead to wildly different outcomes, making long-term prediction practically impossible. This unpredictability is another face of time's arrow, because we can never know the exact position and state of every single molecule in the atmosphere. The future of the weather remains fundamentally open, a path that is created step by step, not preordained. The arrow of time in these systems is a direct manifestation of the same thermodynamic principles we see in a melting ice cube, just operating on a stage of immense complexity. There is a beautiful and paradoxical duality at work here. The universe's overall trend is toward greater disorder, yet within that grand current, the flow of energy through far from equilibrium systems can actually generate stunning local increases in order and complexity. A hurricane is a terrifyingly organized structure, a massive heat engine that thrives on the temperature difference between the warm ocean and the cold upper atmosphere. Its very existence depends on increasing the total entropy of the planet, but it does so by creating a temporary, intricate vortex of wind and rain. This is nature's fascinating compromise. The relentless drive toward chaos creates the conditions for complex, evolving order to emerge on intermediate scales. Our own biosphere is the ultimate example, a vibrant, ever-changing tapestry of life that exists only because it is fueled by the sun's energy, a process that allows for local creativity at the cost of global disorder. We cannot build a time machine, but we can construct experiments that test the very foundations of the arrow of time. The goal is not to reverse the flow, but to scrutinize the laws of physics at their edges, hunting for the subtle cracks where time's one-way nature might be written. These investigations often focus on processes that are almost perfectly time-symmetric, searching for the tiniest of discrepancies. Take the realm of subatomic particles. Certain exotic particles, like neutral K-mesons, exhibit a behavior that is not quite the same when run forward and backward. Their decay reveals a minuscule but measurable preference for one direction of time over the other, a violation of time symmetry rooted in the strange rules of the weak nuclear force. This is not the statistical arrow of thermodynamics we experience every day, but a fundamental, built-in bias at the level of individual particles, a faint whisper of time's arrow inscribed in the fabric of matter itself. Another frontier lies in quantum entanglement. When two particles become entangled, their fates are linked regardless of distance. The process of creating and measuring these entangled states involves correlations that spread and become irreversible, a growth of quantum entanglement entropy that mirrors the thermodynamic arrow. By meticulously studying how these quantum connections form and dissolve, physicists can watch the emergence of irreversibility from the bottom up, observing how the definite world we perceive crystallizes from a fuzzy quantum foundation. We can also look back in time on a cosmic scale. The cosmic microwave background radiation is a fossilized echo of the early universe, a snapshot from when it was just 380,000 years old. This relic light shows a cosmos that was incredibly smooth and uniform, a direct observational confirmation of the low-entropy past that set our entire cosmic story in motion. It is the ultimate empirical evidence for the past hypothesis, a photograph of the universe's improbable starting point. perhaps the most exciting laboratory for these questions is the quantum computer. These advanced machines operate in the realm where quantum weirdness reigns, and researchers are now using them to run simulations that were once pure theory. They can attempt to simulate time reversal for small collections of quantum particles, watching to see how and when irreversibility kicks in. They can study how a small, reversible quantum system, when coupled to its environment, rapidly succumbs to decoherence and begins to obey the familiar, irreversible rules of thermodynamics. In these experiments, we are not watching entropy decrease. We are witnessing the birth of the arrow of time itself, observing how the relentless drive toward disorder emerges from the reversible dance of the quantum world. These tests push empirical science to its absolute limits. They ask not just what the laws of physics are, but why they manifest in the particular, one-way sequence we call history. So why does our memory of yesterday feel so irrevocably tied to the expanding cosmos and the shattering of a glass? The alignment of all these arrows of time is not a cosmic coincidence. It is a cascade of cause and effect, with the thermodynamic arrow, born from our universe's low-entropy birth, acting as the primary driver. Our psychological arrow, the flow of our memories, is fundamentally a thermodynamic process. To form a memory is to create a physical, ordered structure in your brain, a process that requires energy and inevitably increases disorder in your surroundings. You cannot remember the future because that would require a spontaneous, impossible decrease in entropy to create a memory trace before the event has occurred to cause it. The universe's expansion, the cosmological arrow, sets the ultimate stage for this drama. It provides the ever-cooling background, the necessary temperature difference that allows heat to flow and energy to be used. Without this expanding, cooling arena, the universe would quickly reach a bland equilibrium, and the thermodynamic arrow would vanish, taking our sense of a flowing past and future with it. Even the quantum arrow finds its direction here. The process of decoherence, where quantum possibilities collapse into a single reality, is an irreversible spreading of information into the environment. This, too, is a one-way process that increases entropy, linking the fuzzy quantum world to the definite, irreversible world we experience. This beautiful, interlocked coherence suggests that our entire experience of reality, from the galaxies swirling above to the thoughts forming within, springs from a single, unified origin. The one-way street of time is not a collection of separate mysteries, but a single, profound thread woven through every layer of existence, binding the cosmos into a coherent, unfolding story. Our journey through the arrow of time brings us face to face with the ultimate limits of our understanding. We have traced the one-way street from shattered glass to the heat death of the cosmos, yet the deepest questions remain stubbornly unanswered. Why, for instance, was our universe born with that impossibly low entropy, that perfectly stacked deck of cards? The past hypothesis is not an explanation, but a statement of fact, a singular boundary condition that physics cannot yet derive from first principles. It feels like a cosmic favor, a setup so specific it begs for a deeper reason. Was it sheer chance in an infinite multiverse, or does it point to something more profound about creation itself? We simply do not know. This leads to an even more unsettling puzzle. Is the arrow of time a fundamental feature of reality, or is it merely an emergent property, a grand illusion conjured by statistics and scale? Our best candidate for a final theory, a union of quantum mechanics and gravity, might not include time as a primary ingredient at all. It could be that time is like temperature, a property that only manifests when you look at a complex system collectively, emerging from a timeless, fundamental substrate. What then becomes of time in the most extreme environments, like the center of a black hole or the very first moment of the Big Bang? At these singularities, our current laws of physics break down completely. The concepts of before and after may lose all meaning, leaving us with a void in our understanding. The relationship between entropy and time's arrow forces this humbling confrontation. A phenomenon as intimate as the flow of your own consciousness, as undeniable as the march from past to future, remains one of nature's greatest enigmas. These open questions are not a sign of failure. They are the very engine of discovery, an invitation for the next generation to look deeper into the heart of reality and perhaps find the answers that currently lie just beyond our grasp. Our journey has traveled from the shattering of glass to the evaporation of black holes, all guided by the relentless growth of disorder. We have traced the arrow of time from the microscopic dance of particles to the vast expansion of the cosmos, seeing how a simple statistical tendency underpins our most profound experiences. This irreversible flow gives context to our memories, solidifies the chain of cause and effect, and carves out the very possibility of existence in a universe that would otherwise be static and silent. The arrow of time is not a mere feature of our reality, but the fundamental channel through which complexity and beauty can briefly flourish. It is a direct legacy of a special cosmic beginning, a one-time gift of improbable order that allows for everything from swirling galaxies to conscious thought. As you reflect on this profound connection, recognize that every moment you experience, every memory you form, and every choice you make is part of this grand, irreversible current. If this exploration has shifted how you perceive your own place in the cosmos, we would love to hear your reflections. Share your thoughts in the comments, subscribe for more journeys into the heart of existence, and never stop looking up at the stars with